the project milestone 2 that you guys turned in. I'm not sure everybody who's doing the project has signed up for EasyChair. Matt sent an email or a Piazza post about that out on Friday or something. Make sure you sign up for EasyChair if you're doing the project. Even if your partner submitted the milestone to EasyChair, you still need to sign up yourself, because you're going to be asked to write 2 reviews of anonymous reviews of somebody else's project milestone 2. So the process is double blind. You don't know whose milestone you're reviewing. They don't know who you are. And you're only asked to do 2 of them. So as soon as Matt gets everybody signed up who's doing the project, he's just going to randomly assign you to do 2 reviews. And they're very straightforward. So it should take you, you should spend some time reading the milestone, but it shouldn't take you very long to do these. It's not going to be a big amount of work at all. And remember, that's supposed to be helpful feedback for your classmates, whoever's milestone you're reviewing. It's not going to hurt their grade if you give them a bad review, so you don't have to worry about that. What it's going to be used for is the top 12 rated projects in terms of these peer reviews. We're going to take a careful look at, and then we're going to select 6 of them, 6 of the top 12, to give something like spotlight presentations at the end of the semester. So those 6 groups will have more time to talk about their projects than the other. They'll just kind of be given a bit more focus. So make sure to sign up for EasyChair, and then as soon as you do so, Matt's going to send out like 2 review assignments for you guys. Are there any questions about that? Okay. Yeah. Probably, I'm guessing when we get back from Thanksgiving. So, I mean, they shouldn't take you very long. I don't want to tell you to do them quickly, because I want you to take them seriously. But, each one shouldn't take longer than an hour. Read the milestone. So the entire thing should maybe be 2 hours. Read the milestone. There's about 10 questions you have to answer as part of the review. And I think we haven't set a due date yet, but I think that the plan was for them to have to be maybe right after Thanksgiving would be enough time, around then, for us to look at them. But that'll be clear once Matt sends out the Piazza post. So we did these last year. I think they worked out really well. I think people took them seriously, and I was very pleased with the results. And it was kind of fun. You got to see each other's projects in a little more detail. Just to announce it verbally, I said it over Piazza. The final project presentations are now going to be on December 16th rather than 17th, just to check that I have that date right. That's a Wednesday. Yeah, Wednesday, December 16th. So our final class period is actually on Thursday, December 17th. But I couldn't get a room big enough for this what I wanted to do for the final project presentations. So Wednesday's a reading day. There are no finals. And I hope at this point there are no conflicts. I've asked several times over Piazza, and I haven't heard of any conflicts. So that's now when I booked the room for our final project presentations. So the written report's going to be due a couple of days after that, on the Friday, but the actual presentations will be on Wednesday. Okay, so we'll give more details about that as it gets closer, but I just wanted to make you guys aware of that. Any questions about the project in terms of what's to come? Okay, so a few more things. The last homework was assigned. Homework 5 is your last homework. It is shorter than homework 4. It's only 4 questions long, and the programming question is quite easy, I think. So we're trying to give you a shorter homework because homework 4 was long, but also because you're working on your projects now. So you'll probably focus on your projects more now than you were the rest of the semester. So take a look at that. You have the usual amount of time. I think you actually have a little more time for this one because we're not counting Thanksgiving in the 2-week period. So you have like 2.5 weeks. But make sure to take a look at it nonetheless early enough so it doesn't surprise you. Lastly, I wanted to say a few words about the midterm. I was actually quite pleased with the midterm scores. I thought you guys did quite well. The median was 28 out of 45, and given the fact that it was hard and long, I think that's quite good. So overall, you guys did quite well. It was longer than I intended. I think its length was probably on par with the practice midterms length, but maybe both were too long. But given that, I thought you guys did quite well. So I don't think there was a particular question when I looked at the scores that stood out as being one that was you guys struggle with in particular. If you have concerns about your midterm score, or you want to, you want to discuss a particular problem with me in terms of understanding the solution, not the grading aspect, understanding the solution, then please come to my office hours. I'm happy to do that with you. If you have concerns about how your midterm's been graded, then you can ask one of the TAs. They graded the various questions. And the other thing I want to mention, which was something that we did last year, I thought also worked quite well last year, is that we're allowing you to fully correct your midterm. So you're allowed to correct all the mistakes you made, turn it in with homework 5, and earn some number of points back. And however many points you can get back depends on what midterm score you achieved in the first place. So it's like a maximum of 4 points back if your midterm score was below some cutoff, 3 points back if it was in some range, and 2 points back if it was above some cutoff. So the details of that are on the Piazza post. I think that's actually a really good learning tool. Going through the mistakes that you made, correcting the midterm mistakes yourself, I think that's actually not a bad thing to do in general. And if you get a few points back, then it certainly doesn't hurt. So we're not going to release the solutions to the midterm until homework 5 is due, because between now and then you should be looking to correct the mistakes in your midterm. You can still come and talk to me about midterm questions. Okay, I'm not opposed to discussing a midterm question with you. I'm not going to write down the solution for you, but I'm happy to discuss a midterm question, and kind of if you're having trouble understanding one, I'm still happy to do that. This is supposed to be just a learning tool. It's not an exam, this part, yeah.
Yeah, does it include in the bonus question as well?
So the bonus question, no, you don't have to do that one. Yeah. Yeah. With homework 5.
Oh.
So turn it in with homework 5, yeah. Questions? Okay, so we're almost at the end. One more homework project, little test as well. The little test is the other part, but you may not trust me at this point since maybe I said the midterm was not going to be too hard, and it turned out to be harder than I expected. But the little test will be very easy. So we will give you lots of practice with these kind of questions. They're basically the level of the quiz questions. You'll get something like 30 questions at the quiz level. That'll be the little test. Okay. So I decided to break up this week's lecture into half more of a lecture on ADMM and then 1.5 lectures on coordinate descent. I didn't really want to rush ADMM because I think it's such an important topic. Same with coordinate descent. So we're going to have time for one less special topic. I think that's probably fine. And then next week, or maybe even on Thursday, I'll just try to poll you guys to see what you're interested in hearing, because we have maybe more topics than we have time to discuss. So let's go through the motivation for ADMM, and then let's start deriving some ADMM algorithms so we can see just how easy it is to use. So remember that the motivation for ADMM came from optimizing the dual. And we learned that even if you don't know the closed form of the conjugate function, you can still perform something like gradient ascent or the subgradient method on the dual by recognizing this relationship between conjugates, between subgradients or gradients of the conjugate function and gradients or subgradients of your original function. Okay, so this was the key relationship we learned. I mean, you can think about it in this way, actually. This is maybe the easiest way to remember it. If I have a function that's strictly convex, and I ask for the gradient of its conjugate function, then I get that by minimizing my original function minus y transpose z, where the optimization variable here is z, and y is the point at which I want to find the gradient. Okay, so if I can solve this problem, which is a problem that's only defined in terms of f, then I can get the gradient of my conjugate function. So the idea was then to take a problem like this, which was say an equality constrained problem, write down its dual, and recognize that if I want to take a gradient, say, of the criterion here, which require gradients of f star, then I need to know how to basically solve minimization subproblems of this form. Okay, because here I had f of z minus y transpose z to find the gradients of the conjugate function. Here I just have y being minus a transpose u. So to find the gradients of f star, or the gradient of f star evaluated at the point minus a transpose u, I can solve this problem. Okay, this gives me a gradient if this is unique. It gives me a subgradient if this minimizer is not unique. Okay, so this was our understanding here. And then to get gradients or subgradients of my entire criterion, I just apply the chain rule to this part, and this part is just linear. Okay, the optimization variable here being u in the dual. Okay, I had this kind of pervasive typo throughout all of the slides. Thank you for someone pointing it out to me. Everywhere in the slides, after we solved this sub-step for figuring out what the primal update was, x, we didn't carry the most recent one over to the dual update. This used to say xk minus 1. Now it says xk everywhere. So just to be clear, we first solve this kind of primal subproblem, which gives us something like the gradient of our conjugate function evaluated at minus a transpose u. And then we use that to construct a gradient for the dual variable u, and we make an update according to, like, say, gradient descent or the subgradient method, just depending on whether or not that was unique. Okay, so this is really doing, in the case of a unique minimizer for x, we're really doing dual gradient ascent. This is just how we're computing the gradient via this step. Okay, and we can call this x. We saw there's a reason we're calling this x. It's because if x satisfies this this equation here, if x is actually the minimizer of f of x plus u transpose ax, and u was optimal, and u was the dual solution, then x must itself be a primal solution. That just comes from the KKT conditions. So that's why we're calling it x. So we can think about it, this is doing a primal update and a dual update in succession. This is called the dual gradient method. Okay, let's just skip ahead and say that we found this useful because of this property, that using this method allows us to decompose problems in the dual that weren't decomposable in the primal. And this is a very important property that carries over to ADMM. If I have my primal being a sum of functions of blocks of variables, so a sum of fi xi, but I have an equality constraint that ties them all together so that it doesn't really separate in the primal, then we can see that in the calculation of the primal update for the dual gradient method or dual subgradient method, this actually separates across all of the blocks simply because we got rid of the equality constraint. It's turned into a Lagrange multiplier, and this Lagrange multiplier itself can be split up across all of the different blocks. Okay, so I can write this ax as the sum of aixi, blocks of columns times blocks of variables, and then I can realize that actually this is minimizing a sum of functions, each one of a different variable xi, so I can do them separately. Okay, a very simple observation, but it's very important. So this gave us our dual decomposition algorithm, where basically the primal update we could separate out into, say, b different chunks if we had b different blocks of variables, and that is a big reason why we talk about dual gradient methods in general. Okay, because of this feature, this decomposability. So what's wrong with them? What's wrong with them is that they have poor convergence properties. Okay, so we didn't cover that in detail. We saw that they actually have okay convergence properties in terms of achieving the dual optimal criterion value, because they're really just doing something like dual gradient ascent. But they have poor convergence properties in terms of this primal variable. So it's not true necessarily that even if I have my dual iterates converging to the dual optimal criterion value, that these primal iterates will converge to the primal optimal solutions. Okay, they satisfy the stationarity condition in the limit, but it's not really clear that you're going to get there necessarily. That requires maybe some more conditions. And unfortunately, you'll see that in practice, you often don't have convergence of the primal iterates with dual decomposition unless you have kind of rather strong conditions on your problem. So to aid convergence, we saw that there's a technique called the augmented Lagrangian. This technique is also called method of multipliers. Okay, it goes by both names. Both this and dual decomposition are very old ideas. The idea behind this one is to add something to the criterion that gives it some smoothness. gives it extra smoothness, okay, on top of what we already have from the function f. And we're adding something to the criterion that actually doesn't change the problem because of the fact that for any feasible point, ax is equal to b. So this term here, the squared norm of ax minus b, is 0. Okay, but you can see by walking through the steps of the dual decomposition method, or just the dual gradient method for this problem, that this additional term actually does change the algorithm. Okay, because in the primal update, we don't have equality constraints, right? We just had a Lagrange multiplier for those constraints. And you can see that, all right, I've taken the criterion now f of x plus rho over 2ax minus b. I've introduced a Lagrange multiplier u transpose ax for the equality constraint. But this is not the same now as minimizing this when this term is not there. So that term does actually make a difference. Okay. This has much better convergence properties. Yeah. So, I mean, there's still conditions required for this to converge, but in terms of primal iterates converging, this has much better convergence properties. Okay, for one, if this matrix has full column rank, okay, so if A transpose A was invertible, then this is always going to be unique because this term is strongly convex, which means that we're actually doing dual gradient ascent. Okay, so even if f was not strictly convex, we'd still have a unique primal iterate here. Okay, so it adds us some smoothness to the function f and some strong convexity, and it has much better convergence properties. What's the problem? The problem is that we lose decomposability. So even if f split up into sum of functions across blocks of variables, and we could do the same thing here then, of course, we can't do that with this term. Okay, so we lose decomposability in terms of splitting up across blocks of variables. So that's where ADMM came in. ADMM tried to have the best of both worlds. It tried to have this kind of good convergence properties of the method of multipliers, and it tried to have the decomposability of the kind of pure dual gradient ascent method. And one jumping point for ADMM is a problem of this form, just with two blocks. Minimize f1 of x1 plus f2 of x2, subject to a1x1 plus a2x2 equals b. Okay, and we can ask, can we have good convergence properties by adding some kind of augmentation term to the criterion, but still decompose across blocks of variables x1 and x2 when we want to make our primal updates? And the answer is yes. We just force it to be the case. So what ADMM does is it first writes down something called the augmented Lagrangian. It just corresponds to taking the original criterion, adding this same augmentation term that we did before, and then using a Lagrange multiplier for the equality constraint. So this is the usual Lagrangian, right? Criterion plus Lagrange multiplier for our equality constraint. This is just augmenting it. And we repeat the following steps with ADMM. First, we're going to minimize this Lagrangian over x1, fixing x2 at some value and fixing the dual variable at some value. Then we're going to take that value of x1, plug it back in, and minimize the Lagrangian over x2. And then we're going to perform a dual update. So how is this different from the usual method of multipliers? In the usual method of multipliers, we would have replaced these first two steps, where we first optimize over x1, then over x2, by a full minimization over the primal variables x1 and x2. Right? Because this is, together, this actually gives us the proper gradient of, say, f star, evaluated at minus a transpose u. That's just from what we know about the properties of the conjugate function. Separately, this doesn't really give us a proper gradient in any sense, but we're going to do it anyways. That's the way we think with ADMM. We want to decompose the minimization. Let's just decompose it manually into first a step over x1, then a step over x2. Okay, so that's the key difference between ADMM and the usual augmented Lagrangian method. What's the key difference between ADMM and the usual dual gradient method is that we actually have this term. If rho is 0, then we get the usual dual gradient method. Okay, but rho is non-zero. This is a constant, and it augments the criterion and makes it more smooth. Okay, let me pause for questions about that. Okay, so we're going to see in the next, several minutes that ADMM is a very useful platform for minimization. It's very flexible. So it's one of the easiest ways to optimize criterion functions that we often encounter in stats problems or machine learning problems. Okay. We went through this last time. The punchline is that it's has better convergence properties than the regular dual decomposition. Its convergence rate is not known in general, so this is still an open topic. There are certain cases in which it's known. So these authors show that it has a linear convergence rate, so log of 1 over epsilon for certain classes of problems. These classes of problems is a problem class over which first order methods would also get a log 1 over epsilon convergence rate for most of elements of the problem class. So you can think of it as being roughly on par with first order methods, but there's also some thought that maybe they actually perform better than first order methods, and you can see that often in practice as well. Okay, so it's not a first order method because this is not really the gradient, right? This x1, x2 together is not really the gradient, and I'd say that you should try it on your problem and see how it performs for you. But there's some thought that perhaps it performs better than a first order method, but it's certainly in the rough kind of class of algorithms of first order methods, in the sense that it takes a long time typically to get a highly accurate solution, but iterations can be fairly cheap if you set it up properly, and so you use it for problems in which you're not looking for a super accurate solution or it's a large problem. So this is a very useful form of ADMM that we didn't cover, and this is typically how you derive ADMM algorithms, is using what's called scaled form. So we're just going to actually change dual variables from u to u over rho. We're going to call u over rho a new variable, call it w. And it turns out that actually it's quite easy to derive ADMM algorithms in w rather than in u. And this is why. So let's define w to be u over rho. And let's look at a term like this. Let's say u transpose ax plus rho over 2 ax minus b squared. So these are the terms that we would have in the augmented Lagrangian that correspond to our dual variable u. And we're going to try to rewrite these terms in terms of w and not in terms of u. Okay, so I claim that if we actually look at rho over 2 times ax minus b plus w, then subject to terms that only involve u or w, these two are equivalent. So if we're going to minimize something over x or minimize this over x, we're going to get the same thing. So these have the same terms involving x, which means that we could use this instead, as it's simpler to where the dual variable only appears in one term rather than it's often simpler to reduce these two terms to one. Okay, so let's just expand this and we can see why that's true. So I get this term, which I had before, and then I get a this term involving w alone. I don't really care about that because minimizing over x, it doesn't matter that this is here. And the other term I get is this one. I get rho times w transpose ax. Right? That's just the 2 times the cross term. In fact, there's also a minus b here. Okay, but I'm going to throw out this term because it only involves w transpose b. Again, I'm only looking at terms that depend on x. And this guy here, this is equal to rho times w transpose ax. That's just u transpose ax. Right, from the way that I've defined w. Okay, so the conclusion is actually anytime I see these two terms in a minimization over x, I can actually write this term instead. Just remember that w was a scaled version of my dual variable. It's u over rho. So that simplifies my x update quite a bit. And how about for the w update? So before, remember, I had u plus is equal to u plus rho times ax minus b. That was my old dual update. If you look back, let's say how we performed the ADMM steps here. This was just the step size. So what does that mean in terms of w? W plus, I just have to multiply, I'd actually divide everything by rho. Right, this also simplifies the dual update and the scaled variable now. I just add the residual from my equality constraint to w. Okay, so that gives me what's called scaled form ADMM. And although its connection to the method of multipliers is a little bit more hidden, I think it's much easier to remember and to drive algorithms from this perspective. So, okay, I have this problem. Let's go back to our problem. This guy. Minimize f1 of x1 plus f2 of x2 subject to a1x1 plus a2x2 equals b. And scaled form ADMM just basically minimizes the criterion plus this guy over x1. This is just I just do something like this, right? I do x1 plus is the argmin overall x1 of f1 of x1 plus, and now I just have to remember that I have to add rho over 2 times ax minus b plus w. That's going to take the role of these two terms together, right? These two terms together get replaced by this one in the x update. I do the same thing for x2. Okay, I'm dropping the terms of the criterion here that don't depend on what the optimization variable is for these subproblems. Right, the criterion is really f1 of x1 plus f2 of x2, but I can drop one term or the other from these minimizations. Minus b plus w. And then I just do a w update, which is this. Okay, so that's my ADMM algorithm. Very simple. I've just written in the slides with like per iteration notation, just to be clear about the fact that after you solve for x1 here, you plug in the most recent value for x1 in this equation, and then you plug in the most recent value for x1 and x2 in this equation. So the slides have that in a little bit more detail, but they maybe look slightly more complicated than they need to be. This is just the algorithm right here. Okay, scaled form ADMM. Yeah. I mean, so this is supposed to be the most recent x. Okay, so this is actually a1 x1 plus a2 x2, and this one should be a1 x1 plus a2 x2. Yeah. Yeah, so you asked about the order of these? Yeah, the order, it's interesting. The order actually does not lead to the same algorithm, especially when we talk about stopping criterions. So we'll talk about a stopping criterion. You'll see that it's not symmetric with respect to the order of the update, but both are valid. So both algorithms are valid. So usually more important than the order is the choice of decomposition, the choice of equality constraints that we put in the problem in the first place. So we're going to see that, like deriving duals, in order to apply ADMM, we usually have to actually introduce equality constraints. We're going to see that more than the order, those actually have an effect on the algorithm. Okay, so a few practicalities and tricks, and then we're going to go through a few examples. So just to repeat, practical experience is that I think this is a pretty widely held opinion. ADMM usually obtains a pretty accurate solution within a handful of iterations, but convergence to high accuracy is not its strength. So it's more like a first order method than a second order method. And choice of rho, which we didn't talk about at all, rho is the augmented Lagrangian parameter, right? It's like what we put here in the augmented Lagrangian, or here in this form. It's what we put in front of the augmentation term here. that has a pretty big practical influence on the convergence speed of ADMM. The theory says that for any fixed value of rho, it converges. So you have a convergent algorithm, and most of the rates that are derived do not really give a very explicit dependence on rho. So theoretically, it's not clear how rho affects the convergence rate. Any rho will work, but it's not clear how fast it'll converge for different rhos. The one thing that is clear is that when rho is too large, then there's not enough emphasis on minimizing the criterion function. So if we go back to here, or even go back to the augmented Lagrangian, if rho is very large, then there's lots of emphasis on feasibility with respect to that equality constraint. Right? We're trying to make that equality constraint hold true, put a lot of weight on it, and there's not enough emphasis made on minimizing the original criterion function. If rho is too small, then there's not enough emphasis on feasibility. So there's this trade-off, right? We talk about these as primal and dual feasibility. That's the trade-off that rho controls. So in this nice review paper by Steve Boyd, they give a suggestion for how to vary rho from iteration to iteration. I think it actually can be very useful. It's a heuristic, but I think it can be very useful. And it basically checks at every step. It checks whether or not the dual residual or the primal residual is larger. So something like the dual residual you can define in terms of F1 and F2. So something like, are you more primal infeasible or are you more dual infeasible? And then you update rho accordingly. You either make rho bigger or smaller depending on which one is the case. It's a heuristic, and with that choice of rho, actually, you don't have a convergence guarantee because now you're changing rho at every iteration. Okay, so the theory says that rho fixed gives a convergent algorithm. It's not clear what happens if you're changing rho according to the strategy. So that's still pretty much an open question as far as I understand for a practical application of ADMM, how to choose rho. It's not like a step size in the sense of a first order method. We don't have kind of very solid heuristics like backtracking. We just have varying strategies that I think are probably grounded less in theory. So the more important point is that, like deriving duals, transforming a problem into one that ADMM can handle often requires a bit of reparameterization. And if you do that right, then ADMM can be very fast. If you do that wrong, then you might have a pretty slow algorithm. So it matters how you set up the problem in terms of reparameterization. So we're going to go through some examples of that. And then your next homework, or this last homework, has you derive ADMM algorithms for a bunch of problems. Not implement them, but just suggest how you might reparameterize it in order to get an algorithm out of it. So let's skip this. We went through this last time. It's another way of doing alternating projections. I want to go through some fused lasso and group lasso problems because we saw these are actually really quite tricky to optimize with first and second order methods, or at least they required a lot of care. How to set them up, you know, what strengths the various methods had in various cases. We're going to see with ADMM, there's a very simple algorithm for both of them. Okay, very, very simple algorithm for both of them. And this is typically the case with ADMM. Under kind of the appropriate reparameterization, you can get very simple algorithms for complex problems. So remember, the fused lasso was a problem, let's say in the case of regression, where we had a regressor matrix X that was of this form. Minimize some regression loss, y minus x beta, and L2 norm squared, plus some penalty parameter lambda times the L1 norm of d beta. Okay, and d was a difference operator in the fused lasso. It gave us differences of components of beta, say defined with respect to a graph. With respect to this ADMM algorithm, actually, you can just think of it as an arbitrary matrix. It doesn't even have to be a difference operator. Okay, although it will be to our advantage, potentially, if this was structured. So what do? The first thing we do is we just rewrite the problem by introducing equality constraints. Because we have no equality constraints here from the first problem above. There's no way to apply ADMM. So we introduce this equality constraint that alpha must be equal to d beta. So we actually substituted alpha for this entire quantity here, d beta, and the L1 norm. Okay, why do we do that? It's because we might recognize, once we write down the ADMM steps, that actually we know how to solve quadratic plus L1 norm. That's just soft thresholding. Okay, so we wanted to get a variable to replace d beta, so this just looks like the L1 norm of some variable. That was the goal. So we made this substitution, and now we have this problem, right? Minimize 1/2 y minus x beta squared plus the L1 norm of alpha subject to alpha equals d beta. And let's just go through the scaled form of ADMM. First, I got to update beta. I'm going to do beta first, then alpha first, although it doesn't really matter. This has to be given by the argmin over all beta of all the terms in the criterion. I'm going to drop the ones that don't involve beta, so I'm just going to keep the first one, plus rho over 2 times d beta minus alpha. My constraint was that d beta minus alpha was equal to 0. That was my equality constraint. Plus my dual variable w. Okay, so I have to minimize this overall beta. I'm just going to do a few things to move this around. Write this like y minus x beta squared, plus I'll just move the rho in. Okay, so here I'm going to have alpha minus w times the square root of rho minus the square root of rho times d times beta squared. Okay, why did I do it like that? It's because I wanted to get it in a form that looked like just regression. So this is regression of y on x. This is regression of whatever this is. Call it y tilde on, call this x tilde, d times the square root of rho. And so I can think it actually as one big regression where my response is y stacked with this, and then my predictor matrix is x stacked with this on the rows. That's why I wrote it in this form. Alternatively, you could recognize that this is a quadratic. So in order to minimize it, just differentiate it and set it equal to 0. Okay, either way is fine. But this is the beta update. It's easy because it's all quadratics. And maybe being a statistician, I wanted to get it into a form of a sum of two regressions. And then we can read off the solution more or less. It's going to be call the big predictor matrix Z. It's Z transpose Z inverse. Z transpose, call the response B. Okay, so if we just read off what that was in terms of these predictor matrices and responses, you'd see that it was X transpose X plus rho D transpose D inverse times X transpose Y plus rho D transpose alpha minus W. Okay, so that should be the solution. That's our beta update. Okay, so just a quadratic update. Now we have to do an alpha update. So alpha plus is going to be the argmin over all alpha of just the terms in the criterion. Okay, go back to the criterion here. The terms in the criterion that involve alpha plus this guy again, this augmented term. So it's just going to end up looking like the L1 norm of alpha plus rho over 2 times d beta minus alpha plus w squared. And now you can see why I actually wanted to stick in an alpha for the d beta, because I know that this was going to be easy. This is just going to be some kind of soft thresholding. So let me just rewrite that. First I'm going to divide by rho, and I'm going to have this term look like something, d beta plus w minus alpha plus lambda over rho, the L1 norm of alpha. Okay, so now I can see, look, this is just, with respect to this minimization, actually we should be careful here, just to be clear. This is a beta plus. We're using the most recent value of beta. This is just a constant. It's just some number, some vector. So this is just soft thresholding of this vector at the level lambda over rho. That's what the solution is. So I'm going to soft threshold at the parameter value lambda over rho. And what am I going to soft threshold? This vector, d beta plus w. Okay, so the alpha update was quite easy also. And then the dual update, of course, is always easy. We just take w plus d beta plus minus alpha plus. So that's it. That's the algorithm for the fused lasso. Its steps are really quite simple. It can be very efficient. When is it going to be very efficient? It's going to be very efficient when this linear system solve here is structured. So let's suppose x was banded, and let's suppose that d was a difference operator, or even if x was sparse, just x being sparse, then this is a sparse matrix inverse, sparse matrix solve. So this step can be done very efficiently. This step is always trivial. It's just soft thresholding. So in the case that x was sparse, we have a fast fused lasso algorithm. If x is dense, then this is going to be a full linear system solve in a dense matrix. But we could do something like, for example, something that's commonly done. We could compute a matrix factorization of this. So an implementation tip is factorize x transpose x plus rho d transpose d once. So just compute a Cholesky, for example, of this matrix. Once at the very start, first iteration, and then use that Cholesky for all the beta updates. Okay, that's going to be much faster than recomputing a Cholesky at every step. And because this matrix never changes, right, that would be helpful. It's only the right-hand side that changes over iterations. Okay, so relatively simple algorithm for the, say, fused lasso problem class. That's not a special case. That's just the way we're going to see that it turns out if we reparameterize the problem properly. Okay, I'll just say it verbally. What happens if I stuck in, instead of d beta, I actually reparameterize that to be d alpha, and I had the equality constraint that alpha equals beta? Okay, that would actually, I'll let you think about that. That would potentially lead to a hard problem, depending on what d is. So if d was a generic fused lasso operator, that would not be a good idea, because instead of soft thresholding here, I would still have, for this step, minimize lambda times the L1 norm of d alpha plus some quadratic. Even though this quadratic is just a vector minus alpha squared, that could still be hard. Okay, so that would have made our life much harder for this step. We would have had to probably call a subroutine to solve that problem. And if I made a substitution for x beta being alpha, it also would have been a hard algorithm, okay, for the same reason. So this substitution here was actually pretty important. Okay, I basically said all this. So I'm going to skip the group lasso. The group lasso is pretty much identical in terms of derivation. It just requires a substitution for each individual group. And I wanted to get to something else on ADMM, so I'm going to skip that for now. But maybe you can just have it in your mind that it's also a very easy algorithm. It's just a linear system solve. This is soft thresholding as well, but it's just done at a group level. So we shrink all elements of a group to 0 or away from 0, and then the dual update. Okay, so again, a fairly easy algorithm, especially compared to the difficult algorithms we saw with first and second order methods. And this will work for any norm other than the 2 norm, as long as we know its procs. So this, just like it did for the L1 norm, this step reduced to solving for the procs of the L2 norm in this case. So as long as you know the procs, I could change that L2 norm to an L infinity norm. For example, you know its procs. I could have solved that problem just as easily with ADMM. Okay. So this is the last thing I wanted to cover with ADMM, and this is extremely useful. It's called consensus ADMM. Okay, so consensus ADMM is a way of setting up problems for parallelization, even though it looks kind of at first glance like ADMM always has to be performed in serial, right? If you look at these two steps, you can't really ever parallelize these steps. It looks like you might think ADMM always has to be performed in serial, not in parallel or in sequence. I have to perform one and the other. With the right setup, ADMM steps can actually decompose just like the dual decomposition method. Okay, and a problem class for which that occurs is called consensus ADMM. And then there's a bunch of tricks and tips that go along with consensus ADMM. And I think it's emerging as an interesting way to do parallel computation. So if you're more interested in this, then take a look at that the Boyd paper that I referenced that has a bunch of stuff on this. Okay, so let's consider a problem of this form. First, just a bunch of sum of functions of one common variable, x. So the sum of fi of x. Okay, so the variable is common to all the functions, but I have the sum of b functions I want to minimize. So I can actually set up an ADMM algorithm that decomposes, the crucial update here decomposes into b separate minimizations. What I do is I introduce a xi variable for every single one of my fi functions, and I just replace this x, this global x, with a local copy xi, and introduce a constraint that xi must be equal to x. Okay, that's how I reparameterize this problem, and that reparameterization actually makes it so that the x update decomposes over the b chunks. Now I know it's trivial, but this is actually quite neat. Setting each xi equal to a global copy is what allows us to decompose. If we did something like called the if we just defined a different variable for f2 through fb and left the variable for f1 equal to x, then it wouldn't have decomposed that way. Okay, having a global variable that everything is set equal to is what allows us to be decomposable. So this is the problem I apply ADMM to. Now I just apply my scaled form ADMM. I'm going to minimize over each xi variable first. So I just take the terms in the criterion that correspond to xi. That's just fi of xi plus what are the augmentation terms here? This is my problem, subject to xi equals x. So what's the augmented Lagrangian? It's going to be this guy, x1 through xb, x, sum of fi. If I write it in the scaled form, it's going to be this guy. Okay, now this is not a difference from what you saw earlier. This is the same thing. I've just taken these b equality constraints, and you can think about them as follows. It's like this. You can think about that I actually have if I stack them, I have just one global equality constraint like this. And so I have to introduce a dual variable for all of this, call it w, but I'm just naming the components of w that correspond to each of these blocks wi. And so if I were to take this entire vector, x1 through xb, minus this entire repeated copy of x plus w squared, then I can break that up into a sum of squares over all the components. Just take a look at the sum of squares over the first component, second component, etc. That's what this is here. Okay, so this is really nothing else than I could write it like this, x1 through xb minus x plus w1 through wb. It's really just this term, but I've just broken it up across the separate blocks. Okay, so this is the same thing. Okay, so that's my augmented Lagrangian. And now, so consensus ADMM just looks at all the terms that involve xi for a particular I, minimizes those, and look, it decomposes actually across all I. Nicely decomposes. So I just have to perform a separate minimization for xi, And then even though I've updated xi, the important thing is that once I update x1, the minimization for x2 doesn't depend on x1 at all. Right? There's no appearances of x1 in the minimization for x2, for example. So I can perform them all in parallel. It's a very important property. I perform them all in parallel. And then I do an update for x. And this update for x, you can see just by actually looking at this, it's just going to be given by the average of the xi's and the wi's, because this is the only term that involves x. And then I do a dual update for every one of the blocks of my dual variable w. Okay, so in doing this, I can minimize a problem of the form sum of fi of x for a common variable x. It's consensus ADMM. So there's a way. Do you have a question?
I have a question with regard to the group lasso on the previous page. We substituted so we didn't substitute the whole sum. Yes. Are there any cases where that would make sense to substitute the whole term somehow?
Sorry. So this whole term for another variable.
Yeah. I guess that would.
Yeah. So I guess the way we've written it so far, ADMM only takes in equality constraints that are linear. In fact, I mean, it wouldn't. Yeah, we couldn't substitute the whole sum in anyways because that wouldn't be a convex constraint. There are different substitutions to make. The one I wrote down, I think, is just the simplest. So we really did substitute beta for alpha. We made a whole variable substitution, but I just broke up those different L2 norms. Other questions? Okay. So I want to say a few more things about consensus ADMM, and then that'll probably wrap up our treatment of ADMM. So we can see just by these two equations, okay, that actually at every iteration after k equals 1, we're going to have the averages of all the x variables being equal to 0. So this average is just going to be equal to 0. I'm going to note averages in the next slide by bars. Okay, it's because w is being set to be equal to the differences between the xi's and the x's, and so sorry, not this average. This entire dual variable is going to be equal to 0. You can see that just from the definition of w and this update, right? Because I'm just plug in, right, for wi. Just plug in wik minus 1, and you'll see that actually after step k equals 1, we're always going to have this. We're always going to have these two being exactly equal, which forces wik minus 1 to be equal to 0. Okay, so we can essentially write everything in terms of an average notation and get rid of the x update. So here I've simplified these 3 steps into just writing 2 steps in terms of average notation. And so the way to think about the consensus ADMM steps is that I perform an xi update. Okay, I perform an xi update, which is the same as before. I'm going to skip the I'm going to skip this middle update because I'm going to always be setting xk to be equal to the averages of all of the local variables, which I'm going to note by x bar. And then I just do the dual update. Wi gets what it was before plus xi minus x bar. Okay, so this was just a property of those last 2 steps combined. And I think these are quite intuitive to interpret. So first we think about, we want to minimize the sum of functions of a common variable. I introduce local variables for every chunk. I send them off and I ask them to do minimization individually on their own in parallel. So that's the first step. And instead of minimizing fi of xi alone, we're actually adding a term that tries to regularize each of our local variables by bringing them closer to the average. because at the end they have to be in consensus, right? There's only one global variable that I need for all of the different chunks. So here I'm actually penalizing deviations away from the average. So this is kind of trying to push me towards consensus. Plus a dual variable though. Okay, and this dual variable is chosen, you can see based on this step, so that if xi is bigger than the average, then wi is increased, and so we have even more incentive to be smaller. If xi is smaller than the average, then wi is decreased, so we have even more incentive to be bigger. So this dual variable kind of accelerates our convergence to consensus. I think it's a pretty intuitive algorithm. Comes right out of just ADMM. Okay, so it's like doing minimization, but plus some ridge regularization to try to pull us into consensus. There's a more general form of this algorithm that applies with regularization. And this is one that is, I think, like I said, is starting to get some traction about how to do parallel optimization with ADMM. People are kind of interested in this now, and this Boyd paper was the start of some interesting work on this topic. Let's consider a problem of this form. So I actually have minimized fi of ai transpose x plus bi, and I have some other term plus g of x. So I can think of this in a kind of a typical stats or ML setup as this is my loss function. I'm taking a sum here over data points or chunks of data points. This is my regularizer. And maybe in this notation, this linear transformation represents something like covariates times my parameters. Okay, so these AIs could be like my features, and this little x could be like my parameters in a statistics or machine learning setup. You could also just have a generic problem of this form from another application, but this fits nicely with kind of StatML problems. So how do we apply ADMM to this problem? We can do it in a similar way to what we did with the easier problem where we didn't have this linear transformation and we didn't have that, that function g. We're just going to introduce. Okay, I don't know why I had this reparameterization here. I think I just missed the linear transformation and the loss. So after reparameterizing, this is the problem that we're looking at. Subject to each xi being equal to x. Okay, and applying the scaled form ADMM to this problem yields these steps. So minimize only over the xi variable. That I only care about one term in this loss now, and I don't care about this term, and I only care about the one augmented term in xi. So it's a very similar step to before, except we have a linear transformation. That's the only difference. The x update is what's different now, because instead of just minimizing the augmented Lagrangian term, which contains x alone, we also have the regularizer to worry about, this g, the separate g function. Okay, so there's actually two terms, and that's g of x and this term. And I've actually simplified this term just by using the property that you can write the sum of squared norms in terms of a single squared norm with averages. So I just simplified that term a bit. Okay, so that's the x update, and then the dual update is as before. So it doesn't simplify in the sense that we can't get rid of the x update like we did analytically for consensus ADMM without regularization, but it also has the strength that each one of these x updates are performed in parallel. So they can be performed separately in parallel with b separate processors. And now this provides a very interesting way to do parallel optimization for a problem that wasn't parallelizable in the first place. Okay? Again, if I think about these FIs as representing a sum over data points, I can think about this as like this is the logistic loss function or the regression function or something over data points I. X are my parameters, and G is something like the L1 norm or fused lasso or whatever group lasso, some regularizer that you have. Here you've just said solve a ridge penalized problem, so there's no G here at all, separately over the different chunks of data. Look at the prox operator of your regularizer, that's what this is, and then do a dual update. So it's a pretty reasonable algorithm in terms of implementation, and also allows you to parallelize your original problem. Okay, so that's an interesting application of ADMM. Any questions about that? Okay, take a look at that paper if you're interested in more details. And consider it if you're trying a problem of large scale that you want to try to parallelize. I think one of the students in last year's class told me that he implemented consensus ADMM for something in his work, and it sped up his experiment by 16 hours because he was able to parallelize his computation across blocks of data. Okay, let's take a break, and then we'll do a bit of coordinate descent when we get back.